Tim Maudlin is a professor of philosophy at New York University. His books include The Metaphysics Within Physics and Philosophy of Physics, Space and Time. Tim, what is time and how do philosophers and physicists think about time?
Well, I would say the question, what is time, is a bit funny because, of course, the easiest sorts of things where you can answer a question like that are things that are composite or made of other things, and you can, what is a table? Well, it has 4 legs and a top and so on. You can break it down in some way. I think time is a fundamental feature of the physical world. It's a kind of ordering of events, an asymmetric ordering. What I've said is that time is what, in virtue of what events happen in a particular order from beginning to end. I think you're more likely to analyze other things in part of time order than you are to something else. And I think we're all perfectly familiar with the passage of time. So not the kind of thing I think needs a lot of analysis. It's reasonably clear how to represent it mathematically, and physics, because it's involved, concerns things happening in space and time, obviously has to have some kind of representation of time.
It's often said that time is what stops everything happening at once, which is it's a famous saying in physics. But it was actually graffiti in a restroom, as far as I can tell. I looked into that, and John Wheeler was the first one who said that, but he said he found it written in a restroom in Austin, Texas, in a cafe. Time is what keeps everything from happening all at once. And then he added, and space is what keeps everything from all happening to me. Very good, very good. That's a good one. Just to go back to that, so with that in mind, there's often thought that time is an illusion within physics, and sometimes this relates to space-time relativity. How do you feel about time being an illusion? Is this possible, or is it just the way we're defining time? Because as you say, everyone's got an innate understanding of what time is, because me and you have just experienced about 3 minutes now of talking in a passage of time. So how can it be an illusion?
So I think there are a few things that get run together here, some of which you can make sense out of and some of which you can't. If you asked Newton what time was, Newton would have said, well, there are these moments or instants of time, and those are completely global. So you can ask what's happening at a certain moment anywhere in the universe. If I snap my fingers, I can ask, well, what was going on Alpha Centauri right then when I snapped my fingers? And that notion of there being some absolute simultaneity is simply rejected in relativity. So if we think that the theory of relativity is right about space-time structure, then you can say that particular idea of absolute simultaneity, I don't know if the right thing to say it's an illusion, it just doesn't exist physically. But I think that's not the essence of time. As I said, the essence of time is that it orders events, like the snapping of my fingers, and that ordering of particular events is there in relativity just as well. So why it is people say that time as a whole is an illusion, I don't quite understand. I really wouldn't quite know what to make of it. If I thought there isn't really a temporal structure to the world and I'm just in error about that, it seems to me that I wouldn't even know how to begin to do physics, because I have to begin thinking that I know something about the world in order to do physics, and that I can observe certain features of it. And one of the features is time order of events and so on, and how much time elapses between things. These are the sorts of things I take for granted. I'm not really sure it would make a lot of sense to say that physics could show us all of that was illusory.
In terms of time being a fundamental ordering essence, this still applies, as you've just stated, but I just want to clear this up. This also applies to Einstein's space-time relativity, because essentially the issue is where space and time are relative to each other. The future could already be out there. Is this still possible under the ordering of time?
Well, the theory of relativity is, as has been often remarked, a rather bad name for Einstein's theory. You'll often hear that in relativity, simultaneity, say, becomes relative to an observer or something like that. The right thing to say is there just is no such thing in the theory. The theory has a certain space-time structure. It posits that space-time has a certain kind of geometrical structure. That's there independent of observers. It's not relative to anything. And I would say that space-time structure has a time structure in it. The time structure is given only for certain events. There are some events that have no temporal relation between them. Neither happens before or after the other. But for the ones that are temporally ordered, they're ordered in a certain way. And for things like people and clocks and particles that travel along trajectories through space-time, those trajectories have a certain definite length, which you measure in seconds. So the basic geometry of space-time, according to relativity, is actually time structure. The basic geometry of it is given in terms of the structure of time.
Okay, so it's still feasible to say that we have an ordering time structure, even though the future may be out there right now.
Well, out there right now is an odd thing to say, especially the right now part. There is the philosophers sometimes say there's a philosophical sense of is, or a timeless sense of is, which you could translate into is, was, or will be. And if I use that, then I'll say, of course, there is a particular unique past. There is a particular unique future, which is just to say there's one past and there are facts about what it was. There will be one future. There are facts about what it'll be. Does it exist now? Well, if you put the emphasis on now, I would be likely to say, well, the future doesn't exist now just as the past doesn't exist now. But that's to do with the now part, not the exist part.
Thanks for clearing that up, Tim. If we can just change track a little bit now, because on the macro level, you've just explained why time is ordering structure. How does this become different, perhaps problematic, when we deal with quantum physics at a micro level, and how does time operate here?
Well, the question about quantum physics, things become problematic. Anything becomes problematic when you bring in quantum physics, basically because it's problematic to know exactly what you mean by quantum physics or what the physics that's being given by quantum theory. There's a kind of quantum formalism, and there's no general agreement about how to understand it in terms of a clear physical theory. I don't think the issue is microscopic, macroscopic. If there's no microscopic reality, then it's very unclear how you're going to get a macroscopic reality, because you think macroscopic reality just is determined by the microscopic reality, right? You get the macroscopic facts by just generalizing or coarse-graining over the microscopic facts. So in order to formulate quantum theory, you need a space-time structure. Nobody has an idea how to do it without a space-time structure. And if you want to formulate it clearly and precisely and exactly, that space-time structure should be defined at all scales, including the microscopic scale. And to my knowledge, there's no reason to think there's going to be any more difficulty about time at microscopic scale than you would have it at macroscopic scale. Sometimes people somehow think, quantum theory is just about the small and not about the large. But if you think for a second about that, it doesn't make any sense. How can you have implications about the large without having implications about the small? Because the large is just big collections of small things.
You can't obviously have a macro large structure without the micro small structure. But from my understanding of quantum physics, which is rather limited, isn't time essentially different there in terms of a particle being in two places at the same time? Also, quantum gravity seems to operate much differently at these very small micro levels, and isn't generally this kind of mismatch between the large and the small in physics that people are trying to unify with a theory? And if that is the case, then surely that has implications for how we think of symmetry and time at the smallest levels.
Okay, so you mentioned two things there that you want to separate because they're entirely different issues. Whether a particle, or in what sense a particle can be in two places at the same time, depends on having a very clear understanding of quantum theory at all. And different accounts of it, or really what are different theories that are ways of understanding the quantum formalism, can give you different answers to that question. In some it'll be true in some sense that a particle can have no definite particular location at a time. In other understandings of the theory, a particle always does have a definite location. That's just issues about quantum theory on its own. How do you understand it? Then there's a different question, which is how do you reconcile quantum theory with relativity, and especially the general theory of relativity, which is our theory of gravity? Now, it's often said that quantum theory is about the small and general relativity is about the large, but that also, I think, makes no sense. Each theory ought to be about things at all scales. There is gravity at small scales. It's not very much, and you don't have to take account of it often, but it's there. And of course, quantum theory better apply to stars and other very large objects. So it's not so much large and small. There is a question of how do you reconcile gravity with the other forces, where gravity has been treated by general relativity and the other forces have been treated by quantum theory. And there are issues about bringing those two formalisms together. But because no one knows quite how to bring them together, it's very premature to say there's any particular issue about, say, space-time at small scales. If you had a well-defined theory, you might be able to say that, but we don't have one. So whether there's going to be anything strange is going to happen to space-time structure at very small scales, I think is not something we know yet, and I don't really think there are very good reasons to think there's going to be any deep problems there once we do have a theory.
So essentially the issue is about how these forces operate on different scales, but you're saying that this does not necessarily have to affect space and time, even at the smallest level.
Well, what I'm saying is that is leave scales out of it, right? There's an issue of how to bring gravity together with the other forces that we have physics of, the electromagnetic force, the strong and weak nuclear force. We believe these are the four fundamental forces, and we don't yet have a theory that deals with all of them together. But as I say, each force must operate at all scales. So to think that the issue is one of scales, I think, is to misunderstand what the problems are. There are problems reconciling quantum theory with relativity, but that doesn't have to do with scale. Some of it has to do with the so-called non-locality in quantum theory, the violations of Bell's inequality, and how to formulate a theory that gives you those predictions using what kind of space-time structure you need to formulate such a theory. And since relativity is about space-time structure, that brings in relativity. But this really isn't a matter of scales. There are people who think that when you get to very small scales, so-called Planck scales in space and time, that the space-time structure will get very foamy or discontinuous or discretized or chaotic. But as far as I know, there are no more than hand-waving arguments that lead you to that conclusion.
In terms of time and infinity, what can be said about time at the Big Bang, time before the Big Bang, if it's even possible to have time before the Big Bang, and how does this time relate to infinity, either in the past or going forward?
So let's separate a few questions there. If one just looks at general relativity, so leave quantum theory out of it, that's a well-defined theory. It has well-defined equations. If we try to model the universe that we see around us with that theory, it looks like it implies that there was only a finite amount of time in the past, and that everything began, time itself and space-time had an edge or an end to it at a finite period in the past called the Big Bang. And the cosmologists and observational astronomers keep refining how long ago the Big Bang was, and you get closer and closer to agreement on 13.8 billion years, whatever it was. That's using just general relativity, and in that theory, you can't avoid there being a singularity. That is the theory. Well, it looks like the theory breaks down, or if you try to take the theory really seriously, you get to a point where you can't continue further into the past. Now, what we think, of course, is that general relativity isn't exactly right, that eventually we do have to take into account quantum theory. And it may be that that will allow the physics to go before the Big Bang in a very straightforward way, that there really was time and some physical state from which what we call the Big Bang state arose. And if that's true, then there could be time before the Big Bang. And if you ask, well, can it go on forever? The answer is we don't know. You have to look at the theory. As far as I know, there's no reason if you can get through the Big Bang why you couldn't get through anything else and more or less have time going on indefinitely into the past. Nobody's ever had trouble with time going indefinitely into the future. There are some models of general relativity where there would be a singularity to the future, but we have, I guess, no reason to think any of that will happen. So as far as I know, there's every expectation that time will continue indefinitely into the future.
So it is feasible to have time indefinitely and infinitely in the past prior to the Big Bang and also in the future.
Right.
Can you just give me an overview of the field of what you think is going to be on the horizon philosophically, mathematically, and for physicists, the problems we're going to have to deal with in the future when we deal with time?
The biggest technical problem everybody's working on is trying to create a single theory which contains both quantum theory, in particular the theory of electromagnetism and the strong and weak nuclear forces, and general relativity. And that's clearly an issue nobody knows quite how to resolve yet, and that has to be resolved because we know all of these forces exist and they exist together, and there must be some single physics that describes how they all work together. It may be that in bringing those theories together, you're going to have to adjust, well, it's almost certainly the case you'll have to adjust one or both of them. There's a tension between quantum theory because of the non-locality in quantum theory, and this is something that was discovered by John Bell, which is to say quantum theory makes predictions about events or experiments that happen very far away from each other and shows that those predictions require that there be some kind of physical connection or interaction. I'm not quite sure the right word to use, but that experiments done very far apart can't be physically completely independent of each other. And it's not quite clear how to model that if the theory of relativity is correct, because the theory of relativity more or less says that there's no temporal relation at all between events that are very far away from each other. So reconciling that physical connection with space-time structure is something that will have to be dealt with and looks like a fairly hard problem and may require us to actually adjust the picture of space and time we get out of relativity. Sure. Then there are all kinds of just much more technical mathematical questions about making sure the theory doesn't become infinite or blow up or so on. And how those play out, I really couldn't predict at all. They depend on a lot of technical mathematical details of the postulates you're using.
Okay, sure. So just like Newton's theory of gravity was slightly remodified by Einstein, it's possible that we will remodify Einstein's special relativity.
Yes, I think that's something we ought to keep quite open. In fact, if you think about it for a minute, space and time themselves, or space-time structure, isn't directly observable. It's not the sort of thing that you can see or touch or feel or bounce something off of. Our access to space-time structure is always mediated by matter. What we do is what we can observe is how matter behaves, and we make conclusions about space and time themselves, or space-time itself, because we say, well, in order to write down a certain theory of matter, I need a certain space-time structure. And because of that, you might think that our access to space-time structure is sort of indirect, and maybe Einstein didn't get it all right. Maybe there will have to be some adjustments to Einstein's theory when we try to take into account quantum theory and various other things that Einstein himself was unaware of. Einstein didn't, for example, know about Bell's work or Bell's results. He would have been extremely shocked and surprised by them, I'm sure. So I think we ought to keep an open mind. It's an odd sort of thing that many physicists seem so confident about relativity that they won't even listen if you suggest that maybe you need to modify it. But it's hard to see on what reasonable basis you'd think that you'd gotten the space-time theory exactly correct.
How problematic is infinities and a singularity either in the past or the future? Is it acceptable mathematically, or does it show that there may be something wrong in your equations?
Well, what you mean by a singularity is that if you try to continue to solve the equations, the mathematics becomes ill-defined. Certain quantities that have to remain finite become infinite, and therefore the theory just breaks down. Now, there are two ways to interpret that. One is perfectly reasonable, which is to say, well, that's a kind of symptom of a problem with your theory. If your theory has quantities that are increasing without bound, you need to change the theory. The other thing is to say, no, the theory is fine, and that's just saying that space-time itself can't go on, right? There must be an edge or a limit to space-time itself. And that's also a possibility. That was the way most people interpreted the singularity results that you get just by analyzing general relativity. I would think that it's probably more reasonable to expect that if the theory has these singularities, these mathematical singularities, that's telling you your theory's wrong, and you really ought to do something to fix it.
In terms of your work and your future research, what are you working on? What's coming up on the horizon?
Well, what I've been working on for the past 5 years or so is a kind of very large, ambitious project which involves constructing a new mathematical way to represent geometry. Because when we talk about space and time, we're talking about, in a sense, geometrical structure. And we represent that in physics mathematically, so you need a mathematics to do it. And my own view is that the mathematical tool that's been used for the past 100 years to express or represent geometrical structure is the wrong tool. So I've been creating an alternative. It turns out that if you use this alternative mathematical tool, the nature of time, the direction of time sort of pop out at you as being very obvious sorts of things that get represented. And they're rather harder to see if you use the standard mathematical tools. So my hope is that by just rewriting or re-expressing even the theories we have in this new mathematical language, the implications for space-time structure become clearer and a little bit less controversial.
What would the new and alternative mathematics involve methodologically?
So if you ask yourself the following questions, suppose I have a collection of points and I want to make them into a space. I somehow want to give them a geometry so that they get organized and have a kind of spatial structure or spatiotemporal structure. What is the most basic organization that I give to them? In the standard approach of what's called topology, or point set topology, the basic structure is an open set structure. So the picture you have of an open set in space is a set that doesn't have an edge to it or a boundary to it. So if I took a sphere in three-dimensional space and then stripped away the surface of it, just that single infinitely thin set of points that are the surface of the sphere, I end up with an open sphere. It doesn't have a boundary. It doesn't have an edge to it. And that's a standard example of an open set. The usual approach to topology says I organize my points into a space by putting an open set structure on it. And my own view is that that's the wrong structure, that you organize the points into a space in the most fundamental way by indicating which collections of points form continuous lines. So instead of open sets, you have a bunch of axioms about the lines in a space. And then I need to reanalyze a lot of geometrical notions, like what it is for a space to be connected, or what the boundary of a set is, and so on, or the continuity of a function in terms of this new language. It turns out that if you do this, you get a mathematical structure that can deal with continuous spaces and discrete spaces with all the same sorts of forms and definitions, which the standard approach just can't do. And it opens up some pictures of different geometries that one wouldn't have thought of, and rules out certain geometries. So there's a big project, kind of absurdly ambitious one, to rewrite modern physics in terms of this new mathematics.
Okay, the hope, albeit quite ambitious, is to at least get others to adopt this new mathematical method.
Yes, I hope so. I mean, there are certain just straightforwardly mathematical problems and questions that arise once you've defined this and how it relates to the standard way of doing things. In my wildest dreams, what would happen is physicists would say, gee, this actually looks like kind of a better mathematical tool for representing space-time structure than the one we happen to be using. As I often say, you have to understand the feeling of this, you have to think of mathematics as providing abstract tools for physics. And some tools work better and some tools work worse. As I say, if you have a screw and you want to get it into a piece of wood and all you have is a hammer, you can do it, but it's going to be kind of messy and not going to work so well. And if you happen to have a screwdriver, things will go much more smoothly and cleanly. And that's the sort of picture. I think that a lot about, especially relativity, becomes much clearer if you rewrite it in these terms than using the standard mathematical tools.
Is it completely impossible to have a theory of time without mathematics? Surely they seem intertwined.
Well, what happens when you rewrite, space and time get sort of knit together in the theory of relativity. Mm-hmm. So you start talking about space-time structure. And when you then rewrite relativity in these terms, what becomes particularly clear, although it would be clear even in the usual way of doing it, that you can really get rid of spatial structure. You can say the fundamental, most basic form that's giving geometry to space-time is just time. If you more or less tell me all there is to know about temporal structure, you can recover the entire relativistic space-time structure. So in a way, what people often say is that in relativity, time just becomes another spatial dimension, or time becomes spatialized. I think it's just the opposite. If you rewrite relativity in these terms, space sort of goes away or becomes secondary, and what becomes primary is just time as the ordering of events, a certain kind of temporal ordering of events.
Okay, so you're questioning the role of space when we think about time.
Yes, I think if you're going to say anything when you look at relativity, it's that space becomes secondary. What you think of as spatial structure can be defined in terms of time structure, but you can't go the other way around. You can't define time in terms of space.
If that is the case, then how does this relate to the expanding universe, where the rate is getting faster of the expansion, and part of that is the space between the matter in the universe? So from this perspective, it would seem that here space is at least playing a role in time. How would you approach that?
There are two questions in that. Let me separate them. You might ask, well, suppose I just tell you all about times between events. How do you recover our usual talk about space that way? Well, in relativity, built into the foundations of the space-time geometry is a light cone structure. Light plays a very central role in relativity. We all know that. And how do I find out how far something is away from me in space? Well, one thought is this. Send a light ray out and see how long it takes to bounce back to you. So you do sort of radar ranging with light. Well, in order to define that, what did I need? I needed the light, where the light goes, that's given to me by the light cone structure, and I needed the time. How long did it take for the light to go out, bounce off, and come back? So if I just give you a lot of facts about time between events and facts about which events involve light rays, you can recover claims about spatial distance by defining them that way. It turns out if you do this, the speed of light by definition turns out to be constant. That's not a really deep physical fact. That's just follows because you're essentially defining space in terms of time. Now, having done that, you can ask, all right, what's happening to the geometry of the universe and the increasing expansion of the universe associated with the cosmological constant or dark energy, which is, I think, the thing you're thinking about. All of that very naturally can be described in these terms. In fact, the first simplest model of a discrete space-time, a space-time where it's not continuous, that I wrote down and analyzed in these terms happened to be one, I hadn't planned it this way, happened to be a space-time which is expanding in just this way. That once you do the analysis, you would say, oh, this, in some sense, the volume, the spatial volume is increasing at a very rapid rate. All of that is well defined because once I've defined space in terms of time, and I've told you everything that's happening in time, I've told you everything that's happening in space.
Okay, so this can be resolved by how light travels.
Yeah, well, in this, it's because light plays this very central role in relativity, which it doesn't do in classical physics, that you actually have this possibility of only using temporal structure, only using time structure. This is something that happens in relativity and not in classical physics. So, again, this was a surprise to me. It wasn't something I planned, but I started to develop this alternative mathematics, and then having done that in what seemed to me the most natural way, I said, all right, let me rewrite classical physics in these terms, and that comes out in a certain way, and now let me rewrite relativistic physics in these terms, and when you do the relativistic physics, everything becomes very simple and very clean, and the central role of the light cone in the geometry becomes particularly obvious.
As a summary, as a man who specialises in this, if you were to be approached by any random person in a public square and they said to you, what are the most fundamental points of time, what would they be to you, Tim?
Well, I would say time is a fundamental feature of the physical world which orders events in terms of earlier and later. I think the man in the street wouldn't be, or woman in the street wouldn't be at all surprised about that. They'd say, I knew that all along. If you ask me what has physics discovered about it that would be really surprising, it would be, if we take at least relativity as it now stands, that this is a very local thing, that, if you ask me, as I say, if something happens here on Earth and I ask, well, what was happening right then, very far away, according to relativity, there's no fact about that the time structure in a way is more local than you would have thought. Now, having said that, I should say it's not at all clear when we try to bring quantum theory into the discussion that we'll be able to maintain the relativistic picture. We may have to adjust to complete physics. So I think our minds ought to be open that in another 10 years, another 20 years, or 50 years, we'll have yet a different story than the one we have now. But I actually, my own position, oddly enough, especially in philosophy and also when I talk to physicists, is telling people that time is actually much closer to what they thought it was. Sometimes you'll hear physicists and philosophers saying, oh, time's an illusion and we've discovered that time doesn't really pass and so on. And I think all that's wrong. I think time certainly does pass and there's a direction of time and we're getting older all the time and so on. So a lot of things, my own view is much closer to the average person's view than the sort of thing many physicists would say.